Hello everyone, my name is Radwa Chawi, Associate Professor at University of Tartu. Today I'm going to present a paper titled Towards Automated Concept-Based Decision Tree Explanations for a Convolution Neural Network. This work is a joint work with Youssef Sharif and the Professor Sharif Sakr from University of Tartu. Machine learning has achieved great success in lots of application domains, include self-driving car, movie recommendation, face recognition, and healthcare diagnosis. And these machine learning applications are based on training a machine learning model and then train the model to make predictions and decisions. But as a user, I don't know why this model is making this prediction. And even if the model is making the right prediction, I don't know whether the model is making the right prediction for the right reason or not. So here we have a trust problem, and this is a very important problem, especially in critical domains such as in healthcare, when people actually can sacrifice the performance for the sake of transparency. Also, after the general data protection regulations enforced in 2018, it becomes a must for industries to explain the predictions that has been made automatically or any decision that has been made automatically in order to increase the trust. And since then, the topic of machine learning interpretability received great attention. There's no common agreement about a single definition for machine learning interpretability. However, one way to define a machine learning interpretability is the degree to which human can understand and comprehend the decisions made by a machine learning model. And in order to handle the trust problem, we have two ways. One way is to use interpretable models by their nature, such as a decision tree or a a logistic regression model. However, these models fail to achieve the state-of-the-art performance in lots of applications. On the other side, we still can use the black box model and the complicated models such as neural networks, these black box models, and use on the top of it another layer, which may be any interpretability technique that can explain the predictions out of these black box models. And when we are talking about a neural network, one of the state-of-the-art techniques that used to explain neural networks is called saliency maps. And saliency maps works by finding the gradient of the output with respect to each pixel in the image. And by that, we can quantify how important this pixel to the prediction. In this example, we have here two pictures. The first one has been predicted as a cache machine from a network, and this is the explanation of the saliency map. Simply highlights some pixels in the image that, and these pixels tend to be important for the prediction. But if we have a look on this image, it's very hard for us to find, okay, which pixels are more, pixels for the ATM here or pixels for the person, or which concept is more important for the prediction, the ATM machine or the person. In the second example, this is an image that has been predicted as a sliding door from a network. And this is the explanation using saliency maps. But when we have a look on the explanation, it's very hard to say which concept is more important. Is it the envelope or the sliding door? So it would be more useful and more beneficial for the user to quantify the importance or to be able to quantify the importance of each user-defined concept. And actually that has been handled in another concept-based technique called TCAV, testing with concept activation vectors. And in this interpretability technique, instead of trying to understand the importance of a pixel, we here trying to understand the importance of a particular user-defined concepts. So the technique works as follows. Simply, we provide, or the user provide a set of examples for the concepts that he would like to study or that he would like to quantify its importance. So here I would like to quantify the importance of concept stripes. So I form a data set of positive examples with the concept I would like to study, the stripes, and with negative examples, which are some random images. And then I take the activations of these images at a particular layer L, and then I try a linear model that can separate between the class of interest and the random images. And then I get this vector, which is the vector perpendicular on this line. And then I'm trying to get the gradient of the output with respect to this vector, and that quantify the importance of this concept to the prediction. And I can repeat the process for whatever concept I would like to study. But then the problem with this technique is that it's very hard for user to find examples for the concepts that he would like or she would like to study. And also, sometimes we don't know actually which concept is important and which concept we should study. And that motivates us to go to another level of interpretability, which is the automated concept extraction, a technique called automated concept-based decision tree explanations for convolutional neural network. And in this technique, we are trying to extract the concepts automatically from the image and then represent the explanation as a shallow decision tree, such that the node in this tree represents the concepts that are important for the prediction. And if you go through the tree, it's very easy to get explanation using the concepts that are important, and also counterfactual explanation for your instance, means that the concepts that need to be changed in order to change the prediction of this image. Simply, our technique consists of 3 stages. In the first stage, we are given the image that we would like to explain, and then we extract a set of similar images from the training data set to the image that we would like to explain, and then apply a semantic segmentation technique on these images, and then take the activation of these segments from the network, the convolutional neural network we are studying, and then cluster these segments into groups, such that clusters that contains a very few number of examples are ignored because they do not represent a concrete concept that is popular among all the images we use for training. In the second stage, we are trying to learn interpretable concept data. So for each of the clusters we found from the previous stage, we learn a concept detector. The concept detector is simply a linear model that take a data set. This data set consists of positive examples for the concepts that we would like to study, which is the cluster images, and the other group randomly selected images from all clusters. And then we train a linear model in order to be able to detect the presence or the absence of each concept in these images, in these images, the images that are similar to the image I'm trying to explain. So once I do that for all the concept, once I learn a concept detectors for all the concepts formed from the previous stage, I start to here extract concept data from these images. And these concept data come in this form. So simply it's a vector, and the length of the vector is the length of the concepts I extracted. And in each place, I have either a 0 or 1. 0 means that this concept exists. A 0 means that this concept does not exist. 1 means that this concept exists. And I do it for all the images. And in the third stage, I train a decision tree model that is able actually to identify the concepts that are important for the explanation, in addition to also learning counterfactual explanation. You can simply get them from the decision tree, which are the concepts that should be changed in order to flip the prediction. So for example, here we are trying actually to explain why this image has been predicted as a bedroom, and here this is the explanation tree for the image. And if a particular feature can change, or if a particular concept can change, then this image can be predicted as a living room. So our technique provides a way for explaining the prediction as a shallow decision tree. And in this decision tree, you can simply traverse it to find a relevant explanation, in addition to also find a counterfactual explanation.